My today's topic for discussion is lowering of vapor pressure. So I have taken a beaker which has only solvent A particles in my first diagram. That means after evaporation in the vapor phase we will have only A because only one volatile component, that is solvent component, is present here. Then I take a solution where I am mixing A volatile component and B volatile component. So when the both A and B are mixed, in the vapor phase also we will have, because both are volatile, we will have both A and B as shown in this beaker. So at the bottom we have A and B mixture of volatile components. In the vapor phase also we will have mixture of A and B. Now I have taken a system where I have added non-volatile solute particles to the volatile solvent A. Now these non-volatile solute particles will act as a hindrance in the vaporization of A because they will block the surface area. So lesser number of A particles will vaporize and the vapor pressure is expected to be lower, as in this case we have only 4 vapors of A, but when it was only solvent we can see here we have 1 2 3 4 5 6 vapors of A. And when the solution was also volatile, that means both the component are volatile, in that case also we have more A and B volatile particles going in the vapor. Now according to Raoult's law, vapor pressure of solution is equal to the P naught A into XA plus P naught B into XB if the solution is binary, ideal, and it is made up of two components, that is component A and component B. Now in case of lowering of vapor pressure, what happens is that the vapor pressure of the solute component is not counted because solute is non-volatile. So the solute is non-volatile, it will not vaporize, only solvent A will vaporize. That means now in case when we add non-volatile solute in a volatile solvent, the vapor pressure of the solution is equal to the P naught pure vapor pressure of the solvent component into mole fraction of the solvent component. So I can write it like this also, PS P solution divided by P naught A is equal to mole fraction of solvent. Now subtracting 1 from both the sides, I can say 1 minus PS over P naught A. So I am going to subtract 1 from both the sides, that is left hand side also and right hand side also. So solvent. Now we can say that I can write it P naught A into 1 is P naught A minus PS divided by P naught A. So 1 minus mole fraction of solvent is mole fraction of solute, and any property which depends upon mole fraction of solute, that is directly proportional to number of moles of solute. So any property which depends upon number of moles of solute, it is known as colligative property. Now P naught minus, so it is understood that the vapor pressure of pure component will be always more than the vapor pressure of solution where we have a non-volatile solute. So P naught minus PS, this whole term is known as lowering. So lowering is P naught minus PS. But if it is relative to P naught A, that means if I say P naught A minus PS divided by P naught A is relative, because it is relative to P naught A. So it is relative lowering. So if the question is find out lowering, you have to simply find P naught A minus PS. If the question is find out relative lowering, then you have to solve for P naught A minus PS divided by P naught. Now let us try solving this question on vapor pressure. Calculate the mass of non-volatile solute. Molar mass 40 is mentioned in the question, which should be dissolved in 114 gram octane is also mentioned in the question, to reduce its vapor pressure to 80%. That means if initial vapor pressure, so let me consider P naught. So vapor pressure of the pure component, let it be 100. Then when we add non-volatile solute, the vapor pressure of the final resulting solution should be reduced to 80. That means it should become now 80. Now applying the vapor pressure equation. So the equation says P naught minus PS over P naught is equal to mole fraction of solute. So how do we solve it now? So P naught is 100, PS is 80, again P naught is 100. So we have to reduce the vapor pressure to 80. Now is equal to mole fraction of solute means number of moles of solute. So we don't know the mass of solute. Mass divided by molar mass of solute is 40, divided by total number of moles of solution, that is m by 40 plus. Now it is 114 gram octane mass is mentioned, and the molar mass of octane is also 114. So this cancels to be 1. Now when we solve this equation, 100 minus 80. So on solving this, 100 minus 80 is 20 by 100 is equal to, so m by 40 divided by m plus 40 divided by, so on solving the denominator, it becomes m plus 40 divided by again 40. So here 40 40 cancels. So it is 22 by 10, that is 1 by 5. So this is equal to 1 by 5 equals to m divided by m plus 40. So 5m is equal to m plus 40. So 5m minus m becomes 4m is equal to 40. That means m comes out to be 10. Now what is this m? This is the mass of non-volatile solute which we were supposed to solve. So this was the question. Calculate the mass of the non-volatile solute. Now let us discuss Ostwald Walker method to find out experimentally the relative lowering of vapor pressure. So for experimental finding of relative lowering, so here we take two bulbs, A and B bulb, which are interconnected. So A is the solution with non-volatile solute component, and B is the pure solvent A. That means in B bulb, the vapor pressure is due to pure A component, and in A bulb, the vapor pressure is due to the partial pressure of the solution component. So it is being seen in this hypothetical example, the solvent has 3 moles of vapor pressure and the solution bulb has 2 mole. So now we pass dry air first from the solution bulb towards the solvent bulb. So the pure solvent's vapor pressure is 3 and the vapor pressure of the solution bulb is 2. Now when dry air crosses the solution bulb, so it will take 2 A, 2 vapors of A from this A bulb. So 2 vapors of A will go to the dry air, because dry air is now not saturated with vapors. So the A will be lost from the solution bulb. So that means there will be now loss in weight. So there will be loss in weight in bulb A, because its two vapors are gone. Now when it reaches the solvent bulb, now how many more vapors are required? So 3 minus 2 is equal to 1. So already it is having two vapors. Total vapors required was 3. So P naught was 3 and it is already having 2. So now it needs only one more vapor. So now it will take one more vapor. So one more vapor will go from the solvent bulb to the dry air. And that means there is again loss in weight in the bulb. So loss in weight in the bulb B. Now let's talk about this loss in weight. So loss in weight in bulb A. So let me say the loss in weight in bulb A is directly proportional to vapor pressure of the solution, because all two vapors are gone. But loss in weight in bulb B is directly proportional to 3 minus 2. Only one vapor is gone. So that is P naught minus PS. But according to Raoult's law, we need P naught minus PS over P naught. So that is our Raoult's law. So we have PS, we don't have P naught. How to change P naught to PS? Simply do WA plus WB. So this is PS plus P naught minus PS. So PS cancels out. So this is P naught. So we have P naught minus PS as WB, and we have now P naught as WA plus WB. So WA plus WB. So experimentally we can simply calculate the loss in weight of both the bulbs A and B to find out the relative lowering of vapor pressure. So P naught minus PS over P naught is known as the relative lowering of vapor pressure.